Hello, it's Dr. Daystorms, and we've already covered this in class this year so far, but I wanted to go into more detail here and also go over examples other than carbon. And so now we're going to talk about how molecular bonding occurs and how other examples of orbital hybridization. And so, first of all, we can just discuss a little bit about bonding. And when we think about these covalent bonds, we can think of them as the valence electrons, which for hydrogen there's only one electron, but the valence electrons being shared by overlapping of the orbital cloud, the electron cloud, the orbitals. And so, for example, here, if we just had two hydrogens, which each of them only have one electron, as they come together, we have this area of overlap, and this area of overlap is shared between the two, and this is what helps hold them together. And so we get the attraction of one nucleus for the other atom's electrons, and vice versa. Okay. However, if we start to go to the higher level atoms, for example, like chlorine, now we have p orbitals, and then for hydrogen and chlorine, we can see there's an overlap between the sphere of a hydrogen with one of the p orbitals of chlorine, or two chlorines with an overlap of the two dumbbells of the 3p orbitals. But once again, we're only looking at the valence electrons. Okay, so what is it that helps hold these together? Is the fact that they're sharing, there's interaction between the nucleus of one atom with the electrons of the other, and vice versa. And this can only really describe what happens when you have two atoms that overlap, and not something like methane, which is CH4. Okay? So, you can imagine the fact that there's this ideal, if we're just bonding two orbitals, that there's this ideal space that can occur, or that should occur. Because if they're too far apart, in this region of the curve here, the distance between the two hydrogens are too far apart, they're not feeling each other's effect. The binding energy decreases as they start to approach each other, and then there's this ideal bonding space, which for the hydrogen distance, we're talking about 0.74 angstroms, which, remember, 1 angstrom is equal to 1 times 10 to the minus 10 meters. So something that's really, really small. If you get too close, what happens there is if you get too close, the repulsion between the electrons and the electron and electron get too high, and also between the nuclei of the two hydrogens. Because remember, the proton inside the nucleus of one hydrogen will be repulsed by the proton inside the nucleus of the other hydrogen. And so this is the reason why you can't just keep getting closer and closer and closer, and this region of the curve, occurs, because they're going to start to repel each other. Alright, but as we mentioned before, we can't, if we just think of something like methane, which, remember, methane is CH4. And so when we draw the Lewis structure and we want to maximize, according to the V-separ, maximize the repulsion between the electron domains, we can't really imagine the fact that we have to have 4 equal bond lengths. Okay? And because the carbon, remember, its valence electrons, as we mentioned in class, is 2s2, 2p2. So we're going to have some that look like spheres, some that look like dumbbells. Hydrogen, all 4 of the hydrogens would look like spheres. And we couldn't bind those together in some way and come up with 4 equal bonds. Okay? So that's what it means by it's hard to imagine getting tetrahedral, trigonal bipyramidal, and other octahedral, and these other geometries from these atomic orbitals if we don't somehow mix the energies. And so we talked in class about how you can just add a little bit of energy and mix them instead of having s and p orbitals, you can have these sp, sp2, sp3 or hybridized orbitals. And so first we're going to look at beryllium, and look at beryllium chloride, for example, in its electrons. And so here we can immediately, let me actually change this, get rid of the fact that the one s. orbitals, because those are not the valence electrons. The only valence electrons that beryllium would have would be in the 2s, and if you notice, the 2s orbital is already full. Okay, so in its ground state, it cannot form a covalent bond because it has no singly occupied orbitals. So instead, what you can do is if you just give it a little bit of energy, just like what we've been talking about in class, we can take one of these electrons and bump it up into the 2p orbital. Once again, you can ignore the 1s. Okay, and in doing so, we now have two singly or unpaired electrons, one in the 2s suborbital and one in the 2p suborbital. Okay, so you can mix these to make two degenerate orbitals, and these are called sp orbitals because we mixed one s and one p, and they have two lobes. They look considerably, instead of looking like an s orbital, which is a sphere, and a repeat orbital, which looks like a dumbbell, it kind of has this odd dumbbell shape. And so these two sp orbitals, whenever you show together and you only see the large lobes, they look kind of bulbous. Okay, one of the lobes, one of the side of the dumbbell, when we think of it, is much more rounded. Okay, since it's going to resemble more of the S, and the one side is going to be, really kind of tiny. But now what can happen is we can now bind, I said Be, beryllium chloride is actually beryllium fluoride, and we already know from the Lewis structure, we were already expecting it to be, if you remember, to be a linear molecule, like so. And lo and behold, it really is, because now we can have the one electron that comes from the fluorine sharing with one electron from the beryllium into this overlap region of this sp orbital. Okay? And so that's why in class we had mentioned this idea that whenever we have two bonding occur between the central atom and the other one, it could be an sp orbital. For example, with a triple bond here, we have one, oh, that doesn't come through. We have 1, 2 around this carbon electron domains, and so therefore it's going to be an sp orbital. So I actually like to do the electron configuration or the electron energy level domains a little differently than the way that the book has it written, perhaps. And that's because if it was beryllium, we started off like this, where we had 1, 2 electrons, and they were both in the 2s orbital, and we had the empty 2p orbitals. Okay, so then all we had to do was we just had to take a little bit of energy, and if you add enough energy, you can actually pop one of these up here. And so then it would look like we had one in the 2s, one in the 2p, and what we could do is if we just add a slight bit of energy, we can mix these two, and in doing so, instead of having, a 2s and 2p orbitals, we would now have something that's halfway in between. And then we have 2 empty p orbitals, which aren't important here. And these right here would then be called sp orbitals. So now we've got 1 electron from beryllium in each. Whenever we want to bond to the fluorine, which I don't know what color to use for fluorine, but hopefully this will work, we could have the fluorine then coming in and sharing, which that didn't come out very well, did it? The fluorine coming in and sharing, those orbitals in the sp. And this would make a linear, kind of bond. Whoops, fluorine looks like this. Okay, and so we'd have the beryllium in the middle. We'd have fluorine, fluorine, in the beryllium nucleus. So we have a nice linear molecule. We can actually use a similar model for boron. And if you remember, boron actually has 3 electrons. And the books like to show it this way, where we have a 2s, 2 of them in the 2s, and then 1 in the 2p. And if we add a little bit of energy, we can pop it up. So now we have 1 in 2s and 2 of them in 2 individual 2p's. You mix these together to hybridize them, and you get an sp2 orbital. Alright, so if you want to show it in the way that I like to draw it, because that way, at least for me, it's easier to see sp2 orbitals this way. I like to show it in this kind of fashion. So let's clear everything out. We saw the strokes. And so we had originally, here's boron, 2s2. These are the 3 2p's. We add a little bit of energy, and in doing so, we can pop one of those up. So we now have 3 of them. We can now go through and hybridize these, and in doing so, instead of having s and p orbitals, we'll have what's called an sp2. We'll have 3 sp2s and 1 empty p orbital. That p orbital is empty, there's nothing in there. The boron would have 3 electrons, and what are now called sp2 orbitals. Alright, and these sp2 orbitals, for example, could then go on to bond with something like chloride. Because if you know, or if you remember, boron trichloride would look like so with the Lewis structures. Right, and of course we'd have the lone pair electrons, which I can't round each of the chlorides, or chlorines in this instance. Alright, which I'm having problems drawing them in. But each chlorine could then come in and bind here. And so what we would do is we would now then have the what would be the trigonal planar, because you've got the chlorines bonding, sharing some of the overlap with the boron. So there's the boron in the middle, and we would have the chlorines, on each end of the lobes there. And so what that would look like, if they draw it, because they draw it much more pretty than I would, is the fact that we have this these 3 sp2 hybridized orbitals. Okay, and they only show the large lobes there. As we mentioned in class, we can get 4 sp3s with carbon, and you can refer to your class notes and if you would like to see what they look like, but that's how we get the tetrahedral. And we went into great detail on that in class. So to skip ahead, we would see that the tetrahedral shape, which is the common one, for example, that we've seen with methane and everything, where we'd have the carbon in the middle and be able to bond to the 4 hydrogens in the tetrahedral fashion. All right? But we can actually go beyond that by using d orbitals, and so you can imagine getting an sp3d for something that needs to be trigonal bipyramidal, for example. The way that this would look like, if you want to do the energy diagrams, the way that I do the energy diagrams is we would start off, let me use a different color. So we'd have S, P, 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 D. Okay. So you can imagine that by adding energy to where we can get 1 electron into each, for those that have 5 valence electrons. Then, if we hybridize it, we are going to be hybridizing all of these, and we can get 5 1, 2, 3, 4, 5. See, this was the S. These were the 3 P's. That one right there was the D. And now we can get what's called an sp3d hybridized orbital, where we could have 5 electrons that all have the same energy, which is it's more than a P, but it's a little less than a D. And it could go on to form bonds with, 5 other things in order to make that trigonal bipyramidal structure that we talked about last chapter. So this would look like 5 degenerate sp3d orbitals, or you could even go up and do 2 of the Ds in order to make the octahedral, which would be 90 degrees between everything, as we discussed in the last chapter. And just to review everything, okay, so once you know the electron domain geometry, remember, so based on the electron domain geometry, not the molecular geometry, but the electron domain geometry, you can figure out what the orbital hybridization is. So, for example, if you only have 2 electron domains, it's going to be sp. If you have 3, it's going to be sp2. 4 will be sp3. 5 electron domains is going to be sp3d. And if it's octahedral, with 6, it's going to be sp3d2. Hopefully this has helped explain a little bit with respect to orbital hybridization, and especially orbital hybridization for the non-tetrahedral electron domains. I'll see you in class.